A pump is a mechanical device designed to move fluids, liquids or gases, from one location to another. It accomplishes this by adding energy to the fluid, which then results in the fluid's movement through pipes or channels. Pumps are widely used in various industries and applications to transfer fluids for purposes such as transportation, distribution, pressure increase, and more. Pumps operate by creating a pressure difference that pushes the fluid from a region of lower pressure to a region of higher pressure. This pressure difference can be generated through various mechanisms, depending on the type of pump. The main functions of pumps include: fluid transportation refers to the process of moving liquids or gases from one location to another through a network of pipes, conduits, or channels. This transportation is facilitated by the use of pumps, compressors, and other mechanical devices that create pressure differentials to propel the fluid through the system. Fluid transportation is a fundamental aspect of various industries and everyday life, serving essential functions such as water supply. Pumps are used to transport potable water from sources such as reservoirs, lakes, or wells to homes, businesses, and municipal water distribution systems. Sewage and wastewater. Pumps are employed to move wastewater and sewage from homes, buildings, and industrial facilities to treatment plants, where it can be processed and treated. Oil and gas transportation. Pipelines and pumps are crucial for transporting crude oil, refined petroleum products, natural gas, and other hydrocarbons from production sites to refineries, distribution centers, and consumers. Chemical industry. Chemical manufacturers use pumps to transfer various chemicals between processing stages and to deliver finished products to storage or distribution points. Food and beverage production. Fluid transportation is essential for conveying ingredients, liquids, and food products within processing plants, as well as for distributing beverages through bottling and packaging lines. Pharmaceuticals. In pharmaceutical manufacturing, fluids like medications and solutions need to be transported between different processing steps with precision and hygiene. Mining and minerals. Fluid transportation is vital for conveying slurries, solutions, and processing liquids in mining operations, including the extraction of minerals and metals. Energy generation. Pumps and pipes are used in power plants to transport cooling water, steam, and other fluids essential for energy generation processes. Chemical processing. Fluids are transported between reactors, distillation columns, and other processing units in chemical plants to facilitate various chemical reactions and separation processes. Agriculture and irrigation. Pumps play a critical role in distributing water for irrigation in agriculture, ensuring the growth and health of crops. Construction sites often require the transportation of water for concrete mixing, dust suppression, and other construction activities. Marine and shipping. Fluid transportation is integral to maritime operations, including ballast water management, cargo loading and unloading, and vessel propulsion systems. Fluid transportation systems need to be designed carefully to ensure efficient, safe, and reliable movement of fluids. Factors such as fluid properties, flow rates, pressure requirements, and environmental considerations influence the design and operation of these systems. Pumps and related equipment are selected based on the specific requirements of the application, including the distance the fluid needs to travel, the elevation changes involved, and the characteristics of the fluid being transported. Pressure boosting. Pressure boosting refers to the process of increasing the pressure of a fluid to a desired level for various applications. This is typically achieved using pumps or compressors that add energy to the fluid, enabling it to overcome resistance and maintain the required pressure throughout a system. Pressure boosting is crucial in many industrial, commercial, and residential scenarios where adequate pressure is essential for efficient functioning. Here are some key aspects of pressure boosting. Importance of pressure boosting. Water distribution. In water supply systems, pressure boosting ensures that water reaches all points of use, including upper floors of buildings, remote areas, and areas with high demand. Firefighting. Adequate water pressure is critical for firefighting systems to effectively deliver water to extinguish fires. Irrigation. Pressure boosting ensures that water reaches the desired areas for irrigation, preventing inadequate watering and ensuring healthy plant growth. Industrial processes. Many industrial processes require specific pressure levels for operations such as fluid transportation, mixing, and chemical reactions. Hydraulic systems. Pressure boosting is necessary for hydraulic systems used in machinery, construction equipment, and heavy machinery. Sprinkler systems. In agricultural, landscaping, and fire protection systems, pressure boosting ensures proper coverage and distribution of fluids. Pressure boosting methods. Pressure boosting can be achieved using various methods, with the primary approach being the use of pumps. Different types of pumps can be used based on the specific requirements of the application. Centrifugal pumps. These pumps are commonly used for pressure boosting in water supply systems. They use an impeller to create a centrifugal force that increases the fluid's velocity and pressure. Booster pumps. These are specialized pumps designed specifically for pressure boosting applications. They are often used in buildings, residential complexes, and commercial spaces. Multistage pumps. These pumps consist of multiple stages, each with an impeller. Fluid passes through each stage, and pressure is progressively increased. Reciprocating pumps. These positive displacement pumps use reciprocating motion to create pressure. They are used in applications requiring higher pressures or with varying flow rates. Variable frequency drives, VFDs. In some cases, VFDs are used to control pump speed, allowing for variable pressure output based on demand. System design considerations. When designing a pressure boosting system, several factors need to be considered. Flow rate. The required flow rate of the fluid dictates the size and capacity of the pump. Pressure requirements. The desired pressure level and variations in pressure need to be accurately determined. System layout. The layout of pipes, valves, and pumps should be designed to minimize pressure losses and ensure efficient fluid flow. Suction conditions. Suction conditions, including the height of the source relative to the pump and potential cavitation risks, must be addressed. Safety measures. Pressure relief valves and control systems should be integrated to prevent overpressurization. Pressure boosting systems are essential for ensuring reliable and efficient fluid transport, distribution, and operation across a wide range of applications. Proper system design, pump selection, and maintenance are crucial to achieving optimal performance and meeting the pressure requirements of the application. Circulation, in the context of fluid dynamics and engineering, refers to the movement of fluids within a closed system or loop. This movement is often facilitated by the use of pumps, fans, or other mechanical devices that create the necessary flow to ensure even distribution and efficient operation of the system. Circulation serves several important purposes in various industries and applications. Key aspects of circulation. Heating and cooling systems. Circulation is critical in heating, ventilation, and air conditioning (HVAC) systems. Pumps circulate heated or cooled fluid, usually water or a mixture of water and antifreeze, through radiators, coils, or air handlers to transfer heat or cold to spaces for temperature control. Industrial processes. In industrial settings, circulation is used to maintain consistent temperatures within processes involving chemical reactions, heat exchange, and cooling. Liquid cooling systems. Circulation is vital for cooling electronic components, such as in computers and data centers, to prevent overheating. Heat exchangers. Circulating fluids through heat exchangers allows for efficient heat transfer between fluids of different temperatures. Closed-loop systems. Circulation ensures that fluids within closed systems, like hydraulic systems or closed-loop geothermal systems, maintain proper flow and performance. Chemical reactors. In chemical manufacturing, circulation ensures uniform mixing and temperature distribution for efficient reactions. Aquariums and fish tanks. In aquatic environments, circulation pumps help distribute water evenly, preventing stagnation and promoting oxygenation. Water treatment. Circulation is used in water treatment processes to ensure that chemicals, disinfectants, and filtration media are evenly distributed throughout the water. Methods of circulation. Circulation is achieved using various methods and devices, depending on the specific application. Pumps, centrifugal, positive displacement, and other types of pumps are used to move fluids within closed systems. Fans and blowers, these devices create airflow to circulate air within buildings or industrial processes. Agitators and stirrers, in mixing applications, agitators or stirrers are used to circulate liquids and promote uniform blending. Recirculation loops, closed-loop systems with dedicated return lines ensure continuous fluid circulation, maintaining consistent flow and temperature. Impellers and propellers, these components are used in tanks and vessels to create mechanical circulation of liquids. Design considerations. Designing an effective circulation system involves considering factors such as flow rate. The desired flow rate determines the size and capacity of pumps or fans. Fluid characteristics, viscosity, temperature, and chemical compatibility affect the choice of components. System layout, the arrangement of pipes, valves, and devices should minimize pressure losses and promote efficient flow. Residence time, ensuring that the fluid spends enough time in contact with heat exchangers or reactors for effective heat transfer or reactions. Circulation plays a crucial role in maintaining optimal operating conditions, preventing stagnation, and achieving uniform distribution of fluids and temperature within various systems. Proper system design and component selection are essential to ensure efficient circulation and the desired outcomes for the specific application. Dosing and metering. Dosing and metering refer to the precise measurement and controlled delivery of liquids, chemicals, or substances in various industries and applications. The goal is to accurately dispense a specific quantity of a substance over a specified period to achieve consistent and controlled results. Dosing and metering systems are used in industries where accuracy, repeatability, and controlled dosage are critical. Here are some key aspects. Importance of dosing and metering. Pharmaceuticals, dosing is crucial in pharmaceutical manufacturing to ensure accurate formulation of medications and drugs. Water treatment, chemicals for water purification, disinfection, and pH adjustment are dosed to achieve optimal treatment results. Chemical processing, accurate dosing is essential for chemical reactions, ensuring consistent product quality and safety. Food and beverage, flavorings, colorings, additives, and other ingredients are dosed in food and beverage production. Petrochemicals, chemical additives and catalysts are accurately dosed in various refining processes. Agriculture, pesticides, fertilizers, and nutrients are precisely dosed in agricultural applications to optimize crop growth. Laboratory research, precise reagent dosing is necessary for scientific experiments and analyses. Methods of dosing and metering. Peristaltic pumps, these pumps use rollers to compress a flexible tube, accurately metering the fluid without contamination. Diaphragm pumps use a diaphragm to create pressure variations, enabling accurate dosing of liquids. Syringe pumps, syringe-based systems deliver precise volumes of fluids, commonly used in laboratories and medical settings. Piston pumps, positive displacement piston pumps deliver precise amounts of fluid by controlling piston movement. Metering pumps, these pumps are specifically designed for accurate dosing, offering adjustable flow rates and precise control. Mass flow meters, these meters directly measure the mass of the flowing substance, providing accurate dosing information. Design considerations. Designing a dosing and metering system requires careful consideration of several factors. Accuracy, the system must achieve the desired dosing accuracy, often specified in terms of volume or mass. Flow rate, the rate at which the substance is dosed must be controllable and consistent. Fluid characteristics, the viscosity, density, and chemical compatibility of the substance influence the choice of dosing method. Environmental conditions, factors like temperature, pressure, and ambient conditions may affect dosing accuracy. Automation and control, many dosing systems are automated and controlled by programmable logic controllers, PLCs, or other control systems. Calibration and maintenance, regular calibration and maintenance are essential to ensure ongoing accuracy. Dosing and metering systems play a crucial role in industries where precision and consistency are paramount. These systems help achieve consistent results, reduce waste, and ensure the proper use of expensive or potentially hazardous substances. Proper system design, accurate measurement, and effective control are critical for the success of dosing and metering processes. Drainage refers to the removal of excess water, liquids, or other fluids from an area, surface, or system. Proper drainage is essential to prevent flooding, water accumulation, and damage to structures and surroundings. Drainage systems are designed to efficiently channel and redirect fluids away from areas where they can cause harm. Here are some key aspects of drainage. Importance of drainage. Flood prevention. Effective drainage systems help prevent water buildup during heavy rainfall or snowmelt, reducing the risk of flooding. Foundation protection. Proper drainage around buildings prevents water from seeping into foundations, which can lead to structural damage. Land and soil management. Drainage systems are used in agriculture to control soil moisture levels and prevent waterlogging, which can hinder plant growth. Infrastructure protection. Roads, highways, and transportation systems require drainage to prevent erosion and maintain road integrity. Landscape and yard maintenance. Drainage systems ensure that yards, gardens, and landscaping features don't suffer from water stagnation. Methods of drainage. Surface drainage. This involves designing slopes and contours to naturally direct water away from areas prone to flooding or water accumulation. Graded drains. Graded drains are installed at ground level to collect and redirect surface water into underground drainage systems. Trench drains. A trench filled with gravel and perforated pipe is used to direct groundwater away from areas where water pooling is problematic. Sump pumps. In basements or areas with low elevation, sump pumps are used to remove accumulated groundwater and prevent flooding. Stormwater management systems. These include networks of gutters, downspouts, and underground pipes that collect and channel rainwater away from buildings. Retention and detention basins. These structures collect excess water during heavy rainfall and release it slowly, preventing downstream flooding. Erosion control measures. Drainage is crucial in preventing erosion by directing water flow away from vulnerable areas. Design considerations. Designing an effective drainage system involves considering various factors. Water source. Identifying the source of excess water, such as rainfall, groundwater, or runoff, helps design suitable drainage solutions. Site topography. The natural slope and contours of the land influence drainage design. Soil type. Different soils have varying drainage characteristics, affecting the system's efficiency. Volume and flow rate. Calculating the amount of water and the rate at which it needs to be drained guides system design. Infrastructure integration. Coordinating drainage systems with existing infrastructure ensures efficient water management. Maintenance. Ensuring that drainage systems remain clear and functional requires planning for maintenance. Effective drainage systems help manage water in a way that safeguards property, infrastructure, and the environment. Whether in residential, commercial, agricultural, or industrial settings, proper drainage is essential for maintaining safe and functional spaces. Wastewater treatment. Wastewater treatment is the process of removing contaminants, pollutants, and impurities from used water before it is released back into the environment or reused for various purposes. Wastewater includes water from domestic, industrial, commercial, and agricultural activities, as well as stormwater runoff. Proper wastewater treatment is crucial for protecting public health, preserving ecosystems, and ensuring a sustainable water supply. The treatment process involves several stages to effectively remove harmful substances from the water. Stages of wastewater treatment. Preliminary treatment involves screening to remove large objects like sticks and debris, as well as grit removal to separate sand and small particles. Primary treatment utilizes sedimentation tanks to allow heavier solids to settle at the bottom, forming sludge, while lighter materials float to the surface as scum. This removes a significant portion of suspended solids and organic matter. Secondary treatment, biological treatment. This stage uses microorganisms to break down organic matter remaining in the water. Aeration tanks provide an environment for bacteria to consume organic compounds, converting them into biomass and carbon dioxide. Tertiary treatment, also known as advanced treatment, this stage further refines the treated water to meet specific quality standards. Methods may include filtration, chemical treatment, and additional biological processes. Disinfection. Disinfection is the final step to eliminate harmful pathogens and bacteria. Chlorine, ultraviolet, UV, light, ozone, or other disinfection methods are used to ensure the water is safe for release into the environment or reuse. Advanced treatment techniques. Membrane filtration, ultrafiltration, and reverse osmosis membranes remove even smaller particles, contaminants, and pathogens from the water. Nutrient removal. Some treatment plants target nitrogen and phosphorus removal to prevent nutrient pollution and eutrophication in receiving water bodies. Anaerobic digestion. In addition to primary and secondary treatment, anaerobic digestion of sludge produces biogas, methane, and reduces the volume of solids. Constructed wetlands. Natural or engineered wetland systems provide biological treatment by utilizing wetland plants and microbial communities. Advanced oxidation processes. These chemical processes, like ozonation and hydrogen peroxide treatment, break down persistent organic compounds. Environmental benefits of wastewater treatment. Protection of water bodies. Proper treatment prevents contamination of rivers, lakes, and oceans, preserving aquatic ecosystems. Public health. Wastewater treatment removes disease-causing pathogens, reducing the risk of waterborne illnesses. Resource recovery. Treated sludge can be converted into useful resources like biogas and nutrient-rich fertilizers. Sustainable water reuse. Treated wastewater can be reused for non-potable purposes like irrigation, industrial processes, and toilet flushing. Climate impact. Treatment reduces the release of greenhouse gases and prevents nutrient runoff that can contribute to climate change and algal blooms. Wastewater treatment is a vital aspect of modern infrastructure that ensures responsible water management, minimizes environmental impact, and supports healthy communities and ecosystems. Agricultural and irrigation practices involve the controlled application of water to crops and plants to support their growth and ensure optimal yields. Efficient water management is essential in agriculture to meet the water needs of crops, enhance productivity, and promote sustainable land use. Here are key aspects of agricultural and irrigation practices. Importance of agricultural and irrigation practices. Crop growth. Adequate water supply is critical for photosynthesis, nutrient uptake, and overall plant health. Yield enhancement. Proper irrigation can significantly increase crop yields by providing consistent water availability. Drought mitigation. Irrigation helps mitigate the effects of drought by ensuring water supply during dry periods. Food security. Reliable irrigation contributes to stable food production and enhanced food security. Land reclamation. Irrigation can transform arid or semi-arid lands into productive agricultural areas. Types of irrigation methods. Surface irrigation. Water is applied directly to the soil surface and allowed to flow across the field by gravity. Methods include furrow, basin, and border irrigation. Drip irrigation. Water is delivered directly to the root zone of plants through a network of pipes, tubes, and emitters. This minimizes water wastage and enhances efficiency. Sprinkler irrigation. Water is sprayed over crops in a manner similar to natural rainfall. Sprinklers can be stationary or mobile. Subsurface irrigation. Water is applied directly to the root zone through buried pipes or tubes. This method reduces water loss due to evaporation. Fertigation combines irrigation and fertilization by delivering nutrients along with the irrigation water. Design considerations. Designing an effective agricultural and irrigation system involves considering various factors. Crop requirements. Different crops have varying water needs at different growth stages. Soil type. Soil characteristics such as texture and drainage influence irrigation frequency and duration. Climate, evaporation rates, rainfall patterns, and temperature affect irrigation scheduling. Water source. The availability and quality of the water source impact irrigation decisions. Water management. Efficient irrigation methods, such as drip and sprinkler systems, can reduce water wastage. Topography. The slope of the land affects water distribution and runoff. Environmental impact. Proper irrigation practices help prevent soil erosion and nutrient runoff. Sustainable practices. Smart irrigation, using technology to monitor soil moisture levels and weather conditions for optimized irrigation scheduling. Rainwater harvesting, collecting rainwater for irrigation reduces reliance on external water sources. Precision agriculture, applying water and nutrients based on specific crop and soil needs. Crop rotation and cover crops, these practices enhance soil health and water retention. Mulching, applying mulch reduces water evaporation and soil erosion. Agricultural and irrigation practices play a pivotal role in supporting global food production, water conservation, and sustainable land use. Implementing efficient irrigation techniques and adopting sustainable practices are essential to address water scarcity challenges and ensure food security for growing populations. Mining and construction. In both mining and construction industries, the efficient handling of materials, equipment, and resources is crucial to achieving project goals while maintaining safety and sustainability. Here's an overview of how these industries operate and the key aspects involved. Mining. Mining involves the extraction of valuable minerals, ores, metals, and other geological resources from the Earth's crust. This process can have a significant impact on the environment, requiring careful planning, management, and responsible practices. Key aspects of mining include exploration and planning. The process begins with exploration to identify potential mineral deposits. Once identified, detailed planning and feasibility studies are conducted to determine the viability of mining operations. Extraction. Mining methods vary based on the type of deposit, including open-pit mining, underground mining, and mountaintop removal. The extraction process involves drilling, blasting, digging, and transporting materials to processing facilities. Material handling. Conveyors, haul trucks, and other equipment are used to move extracted materials from the mining site to processing plants or storage areas. Processing. Extracted materials are processed to extract valuable minerals and separate waste materials. This involves crushing, grinding, and various separation techniques. Environmental considerations. Mining operations must adhere to environmental regulations and implement measures to minimize their impact on local ecosystems, water quality, and air quality. Construction. Construction involves the design, planning, and execution of projects to build structures and infrastructure. This industry encompasses residential, commercial, industrial, and civil engineering projects. Key aspects of construction include design and planning. Architects, engineers, and planners collaborate to design structures and develop construction plans. Regulatory approvals and permits are obtained. Site preparation, clearing land, excavation, grading, and other activities prepare the construction site for building. Material procurement. Construction materials such as concrete, steel, wood, and various components are procured and delivered to the site. Construction. Skilled workers, equipment operators, and laborers build structures according to the design plans. This involves foundation work, structural framing, roofing, plumbing, electrical work, and more. Project management. Construction projects require careful project management to ensure timelines, budgets, and quality standards are met. Safety. Construction sites prioritize safety through training, protective equipment, and adherence to safety regulations. Sustainability. Green construction practices focus on minimizing environmental impact through energy-efficient designs, use of sustainable materials, and waste reduction. Commonalities and challenges. Both mining and construction industries face common challenges, including safety. Both industries involve hazardous environments and heavy machinery, necessitating strict safety protocols to protect workers. Environmental impact. Both industries impact the environment through land disturbance, resource consumption, and emissions. Infrastructure and logistics. Efficient infrastructure, transportation, and logistics are crucial for moving materials and resources to and from sites. Regulatory compliance. Both industries must adhere to local, national, and international regulations, often involving environmental, safety, and labor standards.
Balancing economic, environmental, and social considerations is essential in both industries to achieve successful projects while minimizing negative impacts on people and the planet.
Sustainable practices and technological innovations are continuously being integrated to improve efficiency and reduce environmental footprint in both mining and construction operations. The oil and gas industry encompasses the exploration, extraction, refining, and distribution of hydrocarbon resources, primarily crude oil and natural gas. It is a complex and critical sector that plays a central role in global energy supply, economic development, and geopolitical dynamics.
Here's an overview of key aspects and processes in the oil and gas industry. Exploration and production.
Exploration: geologists and geophysicists study geological formations to identify potential oil and gas reservoirs. Seismic surveys, satellite imaging, and other techniques are used to locate these resources.
Drilling: once a prospective area is identified, drilling rigs are used to create wells that penetrate the Earth's surface.
These wells can be vertical, horizontal, or directional to access reservoirs.
Extraction: oil and gas are brought to the surface through wellbores.
Production methods vary, including primary recovery, natural pressure, secondary recovery, injecting fluids, and enhanced recovery, advanced techniques like steam injection.
Refining and processing.
Transportation: extracted crude oil is transported via pipelines, ships, or trucks to refineries. Natural gas is transported via pipelines or liquefied natural gas (LNG) facilities. Refining: crude oil is processed in refineries to separate it into various components, including gasoline, diesel, jet fuel, and petrochemical feedstocks.
Downstream operations.
Distribution: refined products are transported to distribution centers and then to gas stations, airports, industrial facilities, and consumers. Petrochemicals: hydrocarbons are used as feedstocks to produce a wide range of petrochemical products, including plastics, chemicals, and synthetic materials.
Challenges and considerations.
The oil and gas industry faces numerous challenges and considerations. Environmental impact: exploration, extraction, and processing can have environmental consequences, including habitat disruption and emissions. Safety: extracting and refining hydrocarbons involve complex machinery and hazardous materials, necessitating strict safety protocols. Geopolitics: the industry is influenced by geopolitical factors, including energy security, trade relationships, and global conflicts. Energy transition: the transition to cleaner energy sources and the mitigation of climate change pose challenges for the industry's long-term sustainability. Technology: technological innovation drives efficiency improvements, safer operations, and new extraction techniques. Regulatory compliance: the industry must adhere to regulations related to safety, environmental impact, and labor standards. Market dynamics: oil and gas prices are influenced by supply and demand factors, economic conditions, and geopolitical events.
Sustainability and future trends.
The oil and gas industry is increasingly focusing on sustainability and adapting to changing energy landscapes. Energy transition: companies are exploring renewable energy investments, carbon capture and storage, and sustainable practices to reduce their carbon footprint. Digitalization: advanced technologies like artificial intelligence, sensors, and data analytics are enhancing operations, reducing costs, and improving safety. Diversification: many oil and gas companies are diversifying their portfolios by investing in renewable energy sources, electric mobility, and other non-traditional sectors. Circular economy: efforts are being made to recycle and repurpose byproducts and waste generated during refining and production processes. The oil and gas industry is at a crossroads, facing the challenges of shifting energy paradigms while continuing to meet global energy demand. Its ability to adapt, innovate, and contribute to sustainable energy solutions will be pivotal in shaping its future role in the global economy.
Medical applications.
Medical applications encompass a wide range of uses for various technologies and practices within the field of healthcare and medicine.
These applications are designed to diagnose, treat, monitor, and improve the well-being of patients. Here's an overview of some key medical applications. Diagnostic techniques.
Medical imaging, technologies like X-rays, computed tomography, CT, magnetic resonance imaging, MRI, ultrasound, and nuclear medicine provide detailed images of internal body structures, aiding in the diagnosis of diseases and injuries. Laboratory tests, blood tests, urine tests, and other lab analyses help diagnose various medical conditions and monitor treatment effectiveness. Genetic testing, genetic analysis identifies genetic mutations, predispositions to diseases, and personalized treatment approaches. Endoscopy, minimally invasive procedures use endoscopes to visualize and examine the internal organs, often used for gastrointestinal and respiratory conditions. Treatment and therapies. Pharmacotherapy, medications are prescribed to treat diseases, alleviate symptoms, and manage chronic conditions. Surgery, surgical procedures range from minimally invasive techniques to complex open surgeries for various medical conditions. Radiation therapy, high-energy radiation is used to target and destroy cancer cells, often in conjunction with surgery or chemotherapy. Physical therapy, therapists use exercises, manual techniques, and modalities to promote recovery and restore function after injuries or surgeries. Rehabilitation programs help patients regain physical, cognitive, and emotional functions after strokes, accidents, or surgeries. Medical devices and technologies. Implantable devices, devices like pacemakers, cochlear implants, and artificial joints are surgically implanted to restore or enhance bodily functions. Prosthetics and orthotics, artificial limbs and supportive devices improve mobility and functionality for individuals with limb loss or physical disabilities. Monitoring devices, wearable devices, such as fitness trackers and medical monitors, help track vital signs, activity levels, and health metrics. Telemedicine, remote medical consultations and monitoring enable healthcare providers to deliver care and advice without physical presence. Digital health and data analysis. Electronic health records, EHRs. Digital records store patient medical histories, diagnoses, medications, and treatments for efficient healthcare management. Health apps, mobile apps offer tools for tracking health, fitness, medication reminders, mental well-being, and chronic disease management. Artificial intelligence, AI, and machine learning, AI technologies analyze medical data for diagnostics, predict outcomes, and assist in personalized treatment decisions. Research and development. Drug development, medical research contributes to the discovery and development of new medications and treatments. Medical devices, engineers and scientists develop new medical devices and technologies to address specific healthcare needs. Medical applications encompass a vast and evolving landscape, driven by scientific advances and technological innovations. They play a pivotal role in improving patient outcomes, enhancing quality of life, and advancing the field of medicine as a whole.